Well, let's say I'm not, so when I insert something in the middle, I don't replace it, I just, create a gap.
Right.
Yeah.
For a lens, it's
Yeah, go on. I wanna hear more. Alright, go on. You should have come early to class, right? Okay. Alright, go on.
like in our lens that we did last class, you could just like have the pointers.
Yeah, shuffle the pointers.
Yeah.
Mhm.
And then it would already inserted.
What about an array?
Um,
Thank you. Alright, okay. Alright, so that's the key word I was looking for. But you all, coming to a solution, and Elena was so close to it, and thank you, peers, okay? That is the biggest reason. And it's such a simple reason. And then, in a few classes from now, or a few months from now, this will be so internalized to you that you won't even think about it, but you'll know, right? So the reason is because in an array, when you stuff something in the middle, you got to shift every other element downstream. So if I want to, right, this is what Elena said. So if I have a billion element array and I want to insert something in the third position, I got to shift a billion minus 3 elements down. Yeah? Okay. All right. So people don't. But if it's only a 5 element array or a 6 element array, it doesn't matter so much. But still, the hassle of having to do that loop to shift everything down is a pain. So whereas in a linked list, it's really simple. You got a new element, and the linked list is there. You don't have to move any of these things. You just come here and just shuffle up your pointer and you're done, right? With local vision, local tunnel vision, you succeed. Whereas with a linked list, you need to have the whole thing. Well, with an array, you need to do the whole thing. So that's the biggest advantage. Okay, now tell me, that's exactly the reason why you would use an array sometimes instead of a linked list, right? So why would you use an array sometimes, right? When you have why don't we always use an array, a linked list? Why do we always use an array? Because a linked list gives you an advantage, right? So Elena just said that a linked list gives you constant time. Because an array, if you want to insert in the middle, the time taken to insert an element in the middle of an array, is it constant time or not? Are you recording this? Yeah? Okay, yeah, thank you. Because this is all important. In 2B and 2C, this becomes increasingly important, right? So these are the kinds, since we don't have anything we've covered all the topics, we don't have to talk about any specific topic, we can talk about all these meta things in computer science, what's useful. So now we've established that, a linked list is useful in certain situations. Yeah? Now, why would you not? So I see that, Elena said there is an advantage into using linked lists because it's constant time insertion. Bam, bam, bam. And I delete things too, like that, right? Constant time. Now, I get that amazing feature and flexibility with linked lists. Why would I ever use an array then? Why don't I just use a linked list all the time? Right? They both give me a collection of items, and they both give me a sequential ordering thing, and a linked list on top of that gives me constant time insert and delete to arbitrary locations in the array, arbitrary locations in the collection, right? So I can say in a linked list, so why would I use an array at all instead of a linked list?
It's just the pointer after that. In arrays, you don't directly access elements.
That's why I do the.
Yeah, go on.
Whereas in
So
a
that's
list,
pointer after.
Yeah.
it takes longer or something.
Why does it take longer? Why does it take longer for a linked list? Because that's exactly the question you'll be asking.
I assume it's when let's say you call element number 7 from a linked list, then it has to shuffle through 7 pointers or whatever
Right.
in order to get there. Whereas in an array, it just gives you the 7 elements.
Thank you. Yeah? All right, did everybody get that? What Pierre said? Okay, that is the advantage of an array compared to a linked list, except it's not shuffle. I don't know if the word is shuffle, but I think I know what you mean here, right? You have to iterate through the first 7. Okay, so yeah, so that's the advantage of an array. An array, if I want the billionth element in an array, I can index arithmetically to it. Bam! Right? Because I know the address of the first element, I know the size of each element. So, a plus nx gives me the address of the nth element. And I can go directly to it, like that. Whereas with a linked list, there's no way. Even if it's a doubly linked list, like Christopher said, right? Christopher and DDA. Are you guys talking about the linked list problem or a Quest issue?
Quest.
Right, Quest, you got to do it in your own time, Christopher. right? Come on over,
It's
right?
It's a linked list too.
It's a linked list.
It's a linked list.
Quest 9.
It's a linked list
We're
question
running
in,
linked
in a
list
quest?
too. Yeah.
Okay, well, anyway, quest number 9 is a totally optional extracurricular quest, okay? So discuss that after, outside of class. But here, here we're having an exciting discussion here because this linked list problem is, Elena came up with a fantastic solution. Pierce, came up with a solution for the opposite side of the problem. When would you use an array instead of a linked list? So you have the option of using both. When would you use an array, right? And so when would you use an array instead of a linked list? So when would you use a linked list?
So you'd use a linked list if you want to have like different like contiguous memory locations. Like it can give you more options for memory.
No, that's not it. Well, what was the solution? What was the solution that Elena said came up with? Right? When would you use a linked list instead of an array? Those are important to know before we start implementing linked lists and arrays, right? Because otherwise, they're both collecting. You won't know which one to use. Put things together. So the crazy thing about computer science today is that there's so many different ways of doing everything. Some are more efficient, some are less efficient. Like I said before, any bozo can design a house or a dwelling, right? You just put some stones together and create a little hole, and you go in there and you shield it from the rain and wind, right? So anyone can do that. An engineer can build it with the least amount of resources, efficiently, right? In the best way possible.
Yeah.
So that's why would you use so you have both arrays and linked lists. They both give you the feature in which you can have access to a collection of items, and they're also ordered with respect to each other, right? So you have that sequential ordering, right? Elena said that you would use an array instead of a linked list because
You would use an array instead of a linked list because, well, actually, Pierce said that one. But
oh yeah, you said the other side. Okay, why would you? It says Lena said you would use a linked list instead of an array because.
Because it's easier to add something in the middle. Because if you want to add something in the middle of an array, you have to shift everything down.
Right, so, which is, very close to what you said, up there, but you didn't quite arrive at it, but you were very close, yeah? Okay, so if you insert something in the middle of the array, you're stuck, right? Because if you have a billion element array, you gotta shift that many elements down, right? So that's the advantage, whereas linked list is constant time, regardless of where you're adding it. Okay, all right, now we wanna know you should have a reason for using this instead of that. If you have a reason for using this and don't have a reason for using that, you'd always use this, right?
Yeah.
It only makes sense. So why would you use an array at all? Why don't I always use a linked list?
I mean, using an array it also like takes up less space because you don't have like two different memory allocations for the data you have as well as the pointer. You just have
Oh, you're saying less overhead. Less overhead per element.
Yeah.
Yeah, okay, all right. That's a valid reason, okay? So that is a valid reason, isn't it? Because in an array, it's very lean. You don't store extra information like pointers to the next guy and all. Effectively, in a linked list, it's at least double, right?
Yeah.
Even if you store characters, I think characters are stored internally as 2 bytes, maybe. I don't know, right? So you're looking at overhead of at least one more pointer.
Yeah.
Okay, but that's not the reason I was looking for, right? So there's one more reason. One more reason why you would use. Didier has a hint for you.
Why don't we just talk about it?
And also like the thing with the linked list is that you can also access 2 different kinds of linked lists through pointers. Like if you want to look at some kind of like pointers.
No. Pierce, no. Alright, Pierce had the answer.
Should I say it?
Yeah, I think you. No, one sec. Hang on. We'll give him one more chance. Okay.
So you were saying?
You were just asking me that question and I told you the answer.
So yeah, while he's coming up with the answer, or while he's thinking it up, those are the questions we want to ask, right? So yeah, Cheyenne.
In general, is like speed better than just.
Oh, okay. So there's
Is speed better than what?
Speed's more important.
here.
Than overhead? That's a fantastic question. That's really a fantastic question to ask. Because in your career as a programmer or a computer scientist or designer or anything, that's a trade-off you have to make every single time you're doing anything at all, because you have multiple ways of doing things. What distinguishes a good product design person, what a good engineer from a bad engineer, is that a good engineer has a good sense, a good intuition of which particular path to take at every point. Right? So here I can use either a hash table or an array or a linked list. Right? Now, and a good engineer thinks, okay, what do I want to get done with this? And what am I going to, so you always make these conscious trade-offs and say, okay, in this place, that's what I gotta use. That place, that's what I gotta use. So if you think about your full product design like that, and you end up with that final product that's really beautiful and slick and fast and efficient to use. People might think there's one path. Here's a need and here's a product, right? You went straight from there to the need. But many people don't realize, especially with a well-designed product, right? Badly designed products, we're not talking about well-designed products. What is not visible to you is that starting from the need, there were 1 billion branching points when you go to the final product. Every single time you could use either that or this. You chose to use this. That or this, and you chose to use that. So there's branching points, so that when you go from the need to the finished product, you can essentially envision 1 billion different products, because there's 1 billion different ways of getting to filling that need, right? Like in life, you have something you need to achieve, and here you are, and then every single day you're faced with a multitude of decisions to make. Should I go to Stanford or Berkeley or Foothill, or should I do computer science or 1A or 2A? So many decisions, right? And as long as you know where you're going, like I keep saying this in 100 different ways, right? As long as you know where you're going, you can make the right decisions, right? So if you have a good intuition about what you want to achieve in life, it's just like making a good product, because you know how to make the best decisions at every point. So you didn't get into Stanford. Okay, well, it doesn't matter. I'll go to Foothill, where you have, Anand's teaching computer science, okay? So, right? So you get this, you make these decisions. All those are now abstracted when you get the final product, right? So later on, in 20 years' time, maybe Cheyenne starts this multinational company with this beautiful product that everybody's raving about, right? And everybody talks about this product in Cheyenne, but they don't know all of the struggles and everything that shaped you into making that product, so that someone else who tries to make the product will never come up with something that is as beautiful, and maybe something that's equally beautiful, I don't know, but they could never end up with the exact same product. Look at genetics, right? It's because every time there's a branch, they might have taken their taste is different, the trade-offs might be different. They might say, I want beauty more than efficiency. Your question, right? So I'm going to trade off in terms of this data structure instead of that, because that is going to be slower, but it will make me give the user a more beautiful experience, right? So you can make these trade-offs, but it's not like you're making these trade-offs willy-nilly, right? You're making these educated, conscious trade-offs. You can always make trade-offs, but you got to make these conscious trade-offs. Don't let the trade-offs, like in Harry Potter, right? Don't let the wand choose the master, right? So the master should choose the wand. Then the wand will do what you want it to do. Yeah? Okay. All right.
Oh yeah, and going back to our question of arrays versus linked lists, arrays already have an index inside them, so it's easier to see where you are in the array. Whereas linked lists, you have to look at.
That's it. That is exactly what Pierce was saying. Yeah. Thank you, Christopher. Yeah, because in an array, you know where to go, and you can get there in constant time. Whereas in a linked list, you got to iterate to get to the element. So when you, and going back to the hash tables, who asked me this question about hash tables? Oh, you asked me the hash tables, right? So if you have a massive data set and you want to index it, not with a number, right? But your index is actually a word. So are you doing, anybody here done Python? Python? So you have this, or a JavaScript, you have this concept called dictionaries, right? A dictionary, you can think of a dictionary as just an array in which the index is not a number, but a string. It doesn't actually have to be a string, it just needs to be a hashable object, right? We haven't covered hash tables, so just to say string, right? So here we have an array that where the index is a string, not a number, right? How can you grok at a data structure like that? So later on, you're going to have to do that, right? Suppose I want to store all the scores for this class, and I don't want to store it by student ID. If I want to store the scores for this class by student ID, that's actually hugely inefficient. Think about it, right? Your student IDs are like 8 digits long. So if I want to make an array, unless I offset it by like 2 billion, it's 2 billion? 2 million, right? 8 digits, 20 million, right? So until I start my array index at 20 million, I'm going to waste a lot of space, right? All of those are going to be empty. Actually, that's not true, because I think there are student IDs less than 2 million too, right? So I'm going to have a huge array with lots of empty spaces. It's a mess. So I might say, well, I don't want to have an array of scores by student ID. I have an array of scores by name. So I can say, what's the score of Christopher? What's the score of Jack, right? Lucy. Ida, right? So I can go by name. How can I create an array? How can I create an array? Here's a question for you. This is not in 2A, right? You don't have to master this for 2A, but these are things you'll think about, whether you're doing 2A or 1A or 3A or Python or JavaScript, right? Even in languages that have a completely different paradigm, declarative languages, right? Even in declarative languages, there is use for arrays in this way. So. Yeah, why would you, hash tables, right? So suppose, how would you solve that problem? I have a dictionary, and I need to index into Cheyenne score. I only have his name, I don't have a student ID, right? So how do I get Cheyenne score from this dictionary? Right, these are just interesting problems. Since we've covered all the material, we're just talking about interesting real CS problems. These are real CS problems. And these are problems that sometime, maybe not now, because these are problems that have been solved like 20, 30, 50 years ago, right? But still, it's good that we haven't, or at least you guys haven't, right? You haven't read about those solutions yet, which is a great stroke of good fortune, really, right? Because you get to look at a problem with fresh eyes. Whereas if you already know the solution, if I've told you what it is, or you've read it online, a Stack Overflow or a book, yeah, okay, you're already starting off with a bias. Right? In science, some of the best hypotheses come out when you don't have any bias at all, right? Because when you don't have any bias, you're just pulling it out of thin air. But if you have a bias, and what I mean by a bias is it's very, very hard in science to come up with a theory with no bias whatsoever, right? Even the best theories have some kind of inductive bias in there. Even if it's a bias like Einstein saw a sparrow fly into his the path of his car when he flew when he drove to work, right? Maybe that had a subconscious bias. It's very hard to come up with a scientific theory without any bias. But let's assume that but when you do come up with something that has absolutely no bias and it actually has corroborations from real life, that gives you a great deal of excitement, right? Because you came up with this. I think I don't know. Maybe it's a hypothesis again, scientific. Maybe it's because you have this feeling that you created something out of absolutely nothing, right? So that's the feeling of true creativity. Because if you have a bias, then you have this niggling doubt in your head. Well, maybe that wasn't truly creative because it was basically it wasn't original. It was basically triggered by something else that entered my mind, right? But if you can't see what triggered you, it was a random neurons in your head. You have more of a justification to attribute it to yourself. Maybe that's the reasoning behind it, right? Evolutionarily. So anyway, let's assume that you have no idea. Yeah, this is the first time you're encountering this problem, and someone says, "I want a dictionary. I don't want an array. I want a dictionary." So one string maps to another string. So how do I get that? Yeah. Okay. So what do you mean by hashing a string?
Well, so like if you have a character, it's just a representation of a specific number, right? And that means that each string, so each character has a
number associated with it,
and you have a string that's a bunch of characters. That means each string has a distinct number associated with it.
Yep.
And you can compare numbers. And there's also like.
Okay. All right. I'm not sure if what he said got recorded on because it's far away. I don't know.
Should have been.
Yeah. Okay. But what Jack is saying really is that every string can be transformed into a unique number. Now, what he said is actually correct in an absolute sense, right? I want us to appreciate that before we go on to a problem with that, and then see how we can address the problem, right? I absolutely love this discussion, right? Because what we did was we started with a big problem, and we're just identifying a solution, identifying a problem with that solution, and then not saying, "Oh, this solution is no good, so we'll toss it out and go back to square one and start again." No, right? So we said we had this problem, and Jack came up with a solution, and we looked at the solution, and we're going to say, "Well, that's a good solution, but it has a problem with it." Right? And I'll tell you what the problem is, and you guys will get a chance to say what the problem is with Jack's solution, right? And then after you find the solution with Jack's, after you find the problem with Jack's solution, you're going to say, "I have a choice. I can either say to Jack, 'Hey Jack, you're totally worthless. Your solution is no good. I'm going to toss it out the window and come up with some other solution. I'll ask Elena, who came up with a beautiful solution before, right? And ask her to come up.' So you can do that, or you can tell Jack, 'Wow, Jack, that's fantastic. I mean, that is the perfect solution I was looking for. It's actually an excellent solution. In fact, it is really an excellent solution, right? However, there is a small problem with it, right? So what is that small problem? Now, when you have that problem, you could say, I'm going to keep Jack's solution because it is so good, and I'm only going to fix that problem. And then you have the benefit of both worlds. You have the goodness of Jack's solution, and also not the weakness of that tiny problem his solution has, right? Now, I don't know, it's all these fields of, knowledge and learning come together in such a beautiful way when you're learning science. That's what I feel. I get a high out of these things, right? Because really, you think about it, that is exactly how science itself evolves. If you look at the philosophy of science, that is how science evolves, because you have a sort of problem, some natural phenomenon that you're not able to explain, right? You say Mercury's orbit should be this shape, but it's not. There's an aberration. You can't explain it. So it's a problem, right? It's a problem. And people come up with solutions. So, or planets go around, the sun in a circle or an ellipse. And someone proposes a solution to it. Newton came up with a solution, saying, there's this thing called gravity, this mysterious thing called gravity that has these invisible fingers, grabbing these planets and whirling them around, right? Essentially, that's what it is. You think about it, right? This is invisible. You can't see it. It's a hypothesis about gravitons. Amazon came out with this graviton processor. Anybody see the press release? Right? They're not happy with Intel's processor. They came out with the graviton processor. What a cool name for a processor. Graviton, since we're going into the age of the singularity, graviton is the ideal name for it to give a processor, right? Especially since Amazon is building out the infrastructure for the singularity. Okay, so where were we going with that? Sorry. Jack's solution, right? So it's in science. You have this theory, and then there's a problem with it. So what happens is that we don't toss the theory immediately, even though we know that Einstein's theory still has a lot to explain. Yeah? There's natural phenomena that Einstein's theory doesn't explain, right? It's quantum level. Take the fact of electrons being hit by photons, right? When an electron is hit by a photon, using mechanics, using the mechanics you've learned in computer, in basic physics, it should be possible to calculate exactly the direction and the velocity of the electron being, so here's a car, and here's a billiard ball, another billiard ball strikes it and it goes in that direction, right? So if you knew the exact velocity and the mass and the coefficient of friction and everything else, right, all the physical parameters, you'd be able to calculate the exact direction in which that ball is going to go after it's been hit. Yes or no? Right? So you can continue to shrink the ball even more. So you can say subatomic levels, the same thing happens. Right? So here's an electron, which is a big ball, and here's a photon, which is a small ball, hits the electron. We know exactly how big the photon is because you know the amount of energy contained in the photon, right? Because you can calculate the energy in the photon, right? This is like wavelength times frequency, is it? Nice, units, right? So you calculate lambda mu. Right. So you calculate, you know the energy in that packet, and so all right. So here's the kinetic energy of the electron. Add the kinetic energy and minus momentum principles and so on and so forth. So you can do that. He was one of the famous nuclear physicists in those times, in Niels Bohr and Heisenberg, and in during that time when exciting things were happening in that area of physics. It's quantum level, right? So Heisenberg said, no, you can't. There's fundamental uncertainty at the subatomic level. Actually, everywhere, but you can observe it at the subatomic. Fundamental uncertainty. What does fundamental uncertainty mean? So fundamental uncertainty means that the universe, nature itself, is acausal at the core. Now, saying something is acausal should basically send every scientist screaming, right? Because if you tell me that nature is acausal at its core, I am, when I hear that, I'm shocked. Right? You're shocked too, because here we are, as humans, we're used to things happening for a cause. If I push Lucy over, she's gonna fall, tip over and fall. And he's gonna say, oh, why did you fall? Because Anand pushed me over, right? So there's always a reason. Anything that happens, we say, oh, that's why it happened. That's why it happened. Sometimes you don't know the reason, but it doesn't say it happened for no reason. You don't say that, right? You say, well, it happened for some reason. I don't know what that is. Yes? But, Heisenberg said, no, there are actually some things that happen with no reason at all. Not that you can't see the reason. Not that our instrumentation is not sophisticated enough that we cannot see the reason yet, but maybe in 100 years' time we'll have a microscope that is so sophisticated and use neutrinos or gravitons that don't affect an electron or even a photon, right? So because the philosophers of those times, Heisenberg's times, they didn't like. Obviously, no philosopher, no scientist likes the fact that nature is acausal, right? Because if you say that nature is acausal, what are you saying? It basically means that humans have no control. There are things that happen without any reason. If there's a reason, I can always manipulate the reason and make it happen like I want it to, right? Or there's at least hope for me to do that. But if I say there are things that you have absolutely no control over, then you don't have a choice. The only choice you have at that point is to basically say, throw in the hat and say, throw in the towel and say, well, I don't know. If I can't control it, I'm just not going to think about it. It doesn't concern me. Right? Isn't that age-old saying, right? Give me the wisdom to change what I can and accept what I can, or something like that, right? So if you can't do anything about it, your best bet is to basically just ignore it, because unless it's gonna, or move away from it if it's gonna cause you pain, right? But you can't do anything about it. So if nature is going to be acausal, I think that sends shivers down the spine of every single scientist I know, right? Because that means there is something in the universe that you can never ever find out. Now, but Heisenberg said, so the philosophers of those times, they said to Heisenberg, no, you're wrong. You're saying that it's acausal only because we don't have microscopes that are strong enough to observe the electron being hit by a photon and not at the same time affect the electron through the act of observation. Because how can you see the electron? The only way you can see an electron is by bouncing something off it, right? But here you're trying to see what the effect of the bounce itself is on the electron. So there's a photon hitting the electron and it's going to bounce off, and you're going to say, I want to see how it bounces off by bouncing another photon on it. That photon is going to send it off in a completely different direction, so you'd never be able to see the original direction, right? So the only way you could potentially, in theory, observe the electron is by hitting it with a particle that is going to hit your retina afterwards, or, right? So it causes a change. It does not cause a change in the electron, but it does have to cause a change in whatever instrument is observing it, because it has to bounce back and hit the instrument and make a change there. If it doesn't make a change there either, you don't see the effect, right? So it's got to make a change here and not here. How is that possible? Right? So, but maybe it is. Maybe in future we would come up with a surface that is able to catch neutrinos. Right? Neutrinos will bounce off the surface, but neutrinos, and cause a change. But maybe they don't change electrons. Right? They go through an electron without making any change to the path of an electron. But in the process of going through it, they absorb some of its wave function or whatever it is, and carry that information through to the diaphragm that intercepts the neutrino. So that's what the philosophers were saying, right? But imagine those days, they didn't know about neutrinos. Maybe they didn't know, but they had the foresight to say that in the future, some alien civilization that is vastly more advanced, right? They would have the instrument necessary for observing an electron under influence of a photonic beam. And so, but Heisenberg said, that is the genius, I think, or not the genius, the foresight. He said, that's okay. I mean, it's entirely possible that, people try what you're saying, but I can prove to you that no matter how sophisticated your instrumentation is, no matter, right, it's some super duper advanced alien race, right, they have an instrument, even then I can prove mathematically that it's still going to be fundamentally acausal. Right, so in fact, he said there are no determinants. If there are determinants and we don't know the determinants, maybe you can find the determinant later on, right? But you cannot determine at all. There's no determinants for that particular physical transformation. So if there are no determinants, bam, so Einstein's theory does not explain a lot of things at the quantum level. Mechanics does not explain a lot of things at the quantum level. So. But that doesn't mean that we're toss Einstein's theory out the window, saying, "Hey, we just found a counterexample, and Einstein's theory does not explain it. So out it goes. Let's start looking for a new theory." No, this is the way science works: is that we'll hold on to it and get it, until we find a better one. We'll hold on to it. So that's the way it works, right? So Jack's solution, coming back, a circle, is, for hash tables, that's a fantastic solution, is to take the string and derive a number from it. It doesn't have to be a string, it can be any object, as long as it's a sequence of bytes, because each byte is basically a number, is a digit in a 256 base number system, right? Each byte has 256 different patterns. So you take a string of bytes, it's basically a number in base 256. So, every string is basically a number. So I could, in theory, even though I'm indexing on strings, I could, in theory, index on numbers by just converting each of those strings into a number. Yes? Okay, good. All right, now we can understand the elegance of John's solution, right? So it's very important, I think, to understand and appreciate the power of a solution before trying to look at any problems it might have. Most of the time, in my experience, what I've found is that there are brilliant solutions people come up with, but programmers, just like humans, ordinary humans, I find they come in two different varieties. Okay, there's a pessimistic kind and there's an optimistic kind. Yeah, so you know what I mean, right? So what I mean by a pessimistic kind is that when you come up with a solution, the pessimistic kind will always look at all the problems first before they look at the positive, the beauty of it, right? And they say, well, yeah, maybe it does it, but there's all these problems, so it's no good. I'm going to toss it out the window, look for a different solution. So, but I think what happens with lots of experience, you code more and more, you look at lots of other people's code, and then you look at that code and say, wow, that is so beautiful. I mean, I spent like 3 pages of writing spaghetti code, and this guy did it in like 10 lines, so beautifully. So you learn to look at beauty and appreciate it. You look at beautiful things. Yeah? So you cultivate your sense of programming aesthetics, and it takes a long time. But after a while, you can see that, okay, that's beautiful, that's not. So even though this is so beautiful and has these problems, I'm not going to fixate on the problems and toss it away. Don't throw the baby out with the bathwater. That's the old saying, right? So you can see the baby. So if you can't see the baby, you can only see the bathwater. Like in those days, I think the story is that the reason the whole married, right? So and so people didn't bathe, and so bathing was a luxury. So this is a story. I may be completely wrong, right? So in a household, the head of the family has the first bath, right? And then the next, this is a pecking order. And the babies apparently were the bottom of the pecking order, so they go in last. And the story is that by the time the baby is put in the bathwater is so murky and dirty that you can't even see the baby. So when you toss it out, the baby goes with it. Now, we think of that and say it's so disgusting and yucky, but if you go back and live in those days, who knows how you think about it, right? You may think that, here's a baby that came out of dirty water, but it's cleaner than it went in before, right? So you actually feel happy. Right? Okay. Because they had different standards of hygiene and things like that in those days. Anyway, so the pessimistic programmer ends up saying, well, not this, not this, not this, not this, not this, and they spend like 90% of their programming time just looking at different alternatives, not settling on anything, right? But an optimistic programmer who always looks at the right, that intuition that maybe comes. I think what happens is that with experience, you get to look past the hurdles because you've seen the solutions of these hurdles, and you say, well, that's not really a problem because I've solved a problem like that 5 years ago. That one I solved 2 years ago. Oh, that one I solved yesterday. So I don't know the solutions, but I know these solutions exist, so I'm going to look past them. So when you look past the solutions, there's a better chance you'll see the beauty at the end, right? And when you see the beauty at the end, that will continue to pull you through the challenges, pull you through the hurdles. And you keep going. But if you lose sight of where you're going towards, then the problems will take center stage and say, hey, you got to do so much hard work to get there, just give it up, right? So and so you've found the problem, but you're now so enamored with the solution's efficiency that you want to make it work with that problem. And so you say, I'm not going to toss out the scientific theory, but I'm going to find a workaround for that little problem. That's a patch. So today, take any scientific theory that we have, it has all these patches, these band-aids, right? This place doesn't work, that place doesn't work, right? Band-aids. What happens if you have too many band-aids, right? Too many band-aids, lots and lots of places where the theory doesn't work. That's when people get unhappy with the scientific theory and say, let's look for a completely new theory which doesn't have any band-aids, right? That's called a revolution in science, right? That's a shift from Newton's theory to Einstein's, or Einstein's to someone else's. So that's a major revolution, paradigm shift in science happens, right? Then like that. So for a hash table, we've got this nice theory, but it's got a problem. What is the problem? So someone tell me what the problem is with Jack's solution, right? Yeah.
Is it if something has the same name?
That's a collision problem. Okay, there's two problems. Now, actually, it turns out that Jack's solution does not have that problem, right? Because Jack's solution says, Every string is a unique number. The only way in which two strings can have the exact same number is when they're the exact same string, right? So because my string is like 577, right? That's a number, 577. This is, ABC is a number, right? Cheyenne is a number, CHAYAN. There's no way another string could have exactly the same number because each is a digit, right? CHAYAN is the only number which will be equal to CHAYAN.
I'm saying like someone's name, Will Smith, and there's another guy named Will Smith.
Yeah, there's two. That's right. You got two people with the same name, right? You can't help it. You gotta have two. You're saying that as long as there are different names, I can handle them all, right? So, but the problem you said is still a valid problem because we had that problem and we had a solution that Jack came up with. That's a fantastic solution. We're going to use that solution. But Jack's solution has a problem, and so we're going to use a solution that's your solution really to address Jack's problem. But your solution also has a problem, right? Which even at that point, we're not going to toss away hash tables. We're still, because hash tables is a beautiful solution, right? So we're still going to hold on to Jack's solution, despite the problem which you solved, despite the problem which your solution has to his problem, right? Despite that, we're still going to hang on to it and still see if we can fix that, okay? So here we are, right? We're designing a sophisticated data structure in class, something you would only do in CS2C. We're designing it in class from the bottom up, looking at a real-world problem, and we're coming up with a data structure, and the importance of this data structure cannot be underestimated, right? So if you only had to master one data structure and be out there in the real world coding for someone like Google or right to AC's, hash tables are one of the most powerful data structures you can use, right? And of course, there's trees and other things, but hash tables are easy and powerful at the same time, and it's used everywhere, right? In fact, when you do Google search, a ton of hash tables are being looked up every single time you type in. Not even every single time you type in a character, because they've got the key up bound, right? So they're doing that immediate thing. So hash tables are so powerful. So what is the problem? What is the problem? Someone tell me what is the problem with Jack's approach, right? Jack came up with a beautiful solution, saying that I can create a dictionary by just using an array in which the index is the number that the string represents. And the number the string represents is basically, that number in base 256. Every character is a 256 base digit. So what's the problem with that? What's the problem? Because if I do that, I get constant time access, right? Anything, someone with a really long name, right, comes up and says, what is my score, right? And I can say, what is your name? That name is exactly this number, and I can pull the score and give it to you. That's constant time, right? Well, it's constant time, meaning it's constant depending on the length of the name, right? So it only depends on the length of the name, not on the size of it. I can have trillions of elements, but I can get to each element in a constant amount of time, right? So, but what is the disadvantage? So every single time when we design something, we got to look at the advantage and also look at the disadvantage. So I say, why should I not use it? What is the problem? What's the problem with doing that, right? So, because at the end, you'll take care of all the problems. You apply patches to all the problems, and you got a finished product. So what is the problem with Jack's approach? What time is it, by the way? I don't know.
9:10.
Wow. Okay. All right. Well, but we're talking about useful, interesting stuff. Unless you guys want to be doing something else. Raise your hand, okay? You're free to do anything if you want, right? So if you're just going to talk. But if you have a specific question to talk about, I can talk about that. So, but what's the problem with Jack's approach? Go on, take a guess. Take a guess.
I was wondering, does his approach involve like making an array from the smallest value of the name to the largest value?
What would be the largest value?
Like whoever has the longest name.
Okay, all right. So it's a pity that Elena's voice is so soft, and I'm not sure if that was captured. It is something the online students absolutely need to listen to and hear, right? So Elena said that the problem with Jack's approach is that someone could have a really long name. You can't say that every name should be like in our pet's quest, 7 characters long, right? You could say that you have a really long name. Now, already in binary itself, 4 bytes is a very long number, right? You cannot on most computers, you cannot have an array or even a vector that has 10 trillion elements on today's computers, right? Because it's not big enough, even on the heap. So if someone comes up with a really long name, and I want to use an array to store that data in the back end, that is a huge number, right, Jack?
That's why you have like a hashing function.
Okay, thank you. All right, so the first solution that Jack proposed is actually the solution, meaning that, you know, what I want to do is I want to use an array, and I want to go from the string to a number, and that number is my index. But I cannot just convert the string directly into a number, because some of those strings will result in enormous numbers that I can't allocate an array for. Yeah? So the problem there now becomes a mathematical problem, because previously in Jack's solution, what I had was a one-to-one map, right? I had a one-to-one map between a string and its corresponding number. Yes? For every string, I guarantee a unique number. Now you're saying, oh no, that's not going to be possible, so we're going to make a compromise. Okay? So here's where the compromise comes in. Here's the trade-offs. So these are the trade-offs that you'll be thinking about all the time when you're creating code, right? So what's a trade-off? What's a compromise? What is a compromise? You know, Jack said we'll use a hashing function. What does a hashing function do? Jason?
Well, couldn't you just take the longest name, and then if you divide all the other names by the longest name, you'd have
A floating
from
point
0
number.
to 1.
Yeah, I get a floating point number from 0 to 1.
Yeah, so then you could just have all the students be a number between 0 and 1.
Well, you know, it's an array, so I presume you're saying take the number from 0 to 1 and then multiply that with the size of the array. So you go from 0 to the size of the array.
Sure.
That's what you're saying.
Yeah.
Right? Because you can't go from 0 to 1. You get a number from 0 to 1, and you want to translate that into an array index.
Yeah, I'm just saying that if you divide it by the largest
Yeah.
number, then you can map the string of the student to the new number. That's much more manageable to index.
Right. So what Jason is saying, so Jason has got a proposal for a hash function. That's exactly what it is, right? So we had a problem, and Jack addressed the problem. Cheyenne came up with a solution, right? And then, oh no, Jack came up with a solution for the problem, and Cheyenne said there was a problem with Jack's solution, and the problem was that, you know, some of the numbers could be big, and then Jason came up with a solution for Cheyenne's problem. And the solution is that let's take that number, enormous number, and divide it by the biggest possible number and get a number from 0 to 1, and then use that to normalize your index, right? So, and then you get a real index from 0 to n. Yeah? So that's a solution. So what Jason has proposed is what is called a hashing function. A hashing function goes from the string to a number between 0 and n. N is the size of the array. Right? So it's predetermined. When you have a hash table, you say this is how big the hash table is, n elements big, right? You can regrow it, but you know what the size is. You know the size of the backing array. So you got the array, and Jason said, given a string, here's how I can generate a number from 0 to n. So Jason has proposed a mapping, right, from a string to a number. What is a problem with that mapping? Right? It's a good solution. That's the way to think about it, right? It's a hashing function. Jason got a solution. He's got a potential hashing function. Because when you got a hashing function, now the question becomes, how can I pick a hashing function? How can I pick a good hashing function? So Jason said, well, here's a good hashing function. And he said, you know, here's how you convert that number into an index. So he came up with a solution. So here's how we're designing this data structure in a group. This big class here is designing one data structure. Because that's how software engineering should be, right? You're all sitting in a room, there's this product, this is, you know, and we're trying to design it, and we're thinking, oh, there's a problem with that, and someone else says, oh, well, let's fix that problem this way. So think about it, how exciting it will be later on when you're sitting and designing a product together, right?
Well, the problem with his solution would be that floating point numbers are imprecise.
It's imprecise, yes,
So
yeah.
if you did that division and then you multiplied out, you might not end up with the same number that you would expect.
But that's the case with many hashing functions, right? I could have another hashing function also, even our existing hashing function, even though the likelihood is very low, it's possible that, you know, the moment you've converted from that size to this size, automatically you know it's lossy. Some information has been lost, right? Because you got a TIFF file that's this big, and then a JPEG file that's this big. Right, it's lossy. You cannot recover. Well, you can with, you know, you cannot recover. You can reconstruct it to the best of your hypothesis, you know, or knowledge of what it might have been using machine learning, but you cannot get the original back because it's lossy. right? When everything goes into a black hole, there's no way you can get the whole universe back because it's lossy, well, according to the theory anyway, right? So it's lossy when you go from a big space to a small space. So what is the question? You're going in the right direction, you know, and Jack is going in the right direction. What is the problem? So Jason came up with a hashing function. What's the problem with that? So it turns out that, you know, Jason's function is a reasonable, now I'm not saying good, but it's a reasonable hashing function because that's where you start. Because now we've met the goal, or solved the problem of not having to have a ginormous array, right? I can have an array of only n elements, and n is something that I can afford, right? I can only afford an array of 10,000 elements in a small computer. So I say n is 10,000. On a big computer, maybe 10 billion elements, or it's 10 trillion elements. So I know n beforehand. I've decided that's what I'm going to use. And Jason said, from a string, here's how you turn that into a number from 0 to n, right? So he said that. So so now the question becomes, how do I design a good hashing function? Now, so the issue really with hashing functions, and the reason it's not so easy, it's not trivial, right? Even in 2C, we don't cover hashing functions in great detail because designing hashing functions is an entire field of research in its own right. People have spent years just thinking about how to come up with good hashing functions. Yeah, I think Knuth wrote an entire chapter in fundamental algorithms, right? Of how to come up with good hashing functions. Because a hashing function has to give you a map, a value, a number, in which the likelihood of a collision is very low, or as low as you can get. Right? Meaning that two strings come up with the same number. Now it's possible, using that approach, that two different strings, because you're losing a lot of information, right? Two strings have the same, quotient when you divide, they'll end up with the same number. So what we have now is a many-to-one mapping, right? It's not a one-to-one mapping. Previously what we had was a one-to-one mapping, right? Like that. Now we have a smaller space of indices, so necessarily you have to have many-to-one, right? Some of these will map to 1, some of these will map to, right? So you have a many-to-one mapping. So in other words, you run the risk of what is called a hash collision. Now let's say that Ida and Elena have the same hash value based on my function, right? Or based on Jason's function, right? So Jason said, add the characters, divide by n, and that number tells you, scale it to 0 to n, that gives, right? So I use Jason's technique, and it gives me the exact same number for both Ida and Elena. So when Ida comes to me and says, what did I get in my last assignment? And I look it up and I come up with Elena's score and I tell her, right? So it's a huge confusion there. So that's the risk, isn't it? That's called a collision. So a hash function is designed in such a way as to minimize the risk of collision. Right? So you want to minimize the risk of collision. So how would you minimize the risk of collision? It turns out one of the best ways, if you don't have any knowledge of the domain, right? So sometimes you have a knowledge of the domain in which your hash function is going to be applied. For example, if I know that it's going to be applied to student names, if I know it's going to be applied to certain things, then I can design the hash function in such a way that in that domain I get a good distribution, right? This is something I don't know anything about the domain. It's all truly random bytes. How would I design a good function, a hash function, such that the many-to-one map, even though it's many-to-one, gives me the minimized collision risk. In other words, if you can quantify the risk of collision, right? So if I say this is the risk of collision, right? RC. If there is a function that minimizes the risk of collision, and you can somehow, let's say, is some function of some variable x, right? Some variable, x could be the size of the string, or some internal parameter in your hashing function, right? So you want to do that. What do you want to do? So you want to minimize the risk of collision. Right? So essentially the same as in mathematics. This is what you do in some machine learning algorithms like gradient descent, for example, right? Gradient descent is you define the surface of the area as a surface. Because the surface is undulating and goes up and down, you want to minimize the error. You find the slope of that surface at any time, and then the slope will tell you in which direction you should change the parameters so that you move in the direction of the minimum, right? So if you have a curve like that, and you want to find the minimum here, and you start here, how do you find the minimum value, right? And you calculate the slope here. And the slope, if the slope is positive, then you go to the right. If the slope is negative, you go to the left. Yeah? And you don't take big steps, you take tiny steps so that you don't overstep a minimum or maximum, right? So you take tiny steps, iteratively you can end up in the minimum. So that is called gradient descent. You know, very commonly used or used to be used a lot in machine learning. You know, now you can use it in, you know. So that's, so you may want to do something like that to minimize the risk of collision. But most of the time, if the bytes are truly random out there, and you want to hash that, a good way is to say that I want a function that basically just gives me a checksum that is as uniform as possible over the space. In other words, I give you numbers that are very tightly related to each other. Let's take, you know, the digits of pi, right? I want to find a hash of 3, a hash of 1, hash of 4, hash of 1. So like, you know, see some pattern. Even though you give the hashing function a list of strings in a predictable pattern, like A, ABC, ABCD, and so on and so forth, predictable pattern. Even then, even though A is right next to B or B comes after A, the hash values of A and B should be like totally unrelated. They should be random. So the distribution, there should be no pattern in the hash values. In other words, if you supply a pattern to the hashing function, that pattern should be completely destroyed when it comes out the other side. So that is a hallmark of a good hashing function. So a hash function is chosen in such a way that it returns a value that is, you know, you can check it out. So if you go on, I'll go to Google or you know, just open up a terminal. Maybe I'll do it. Yeah, well, I'll pull it up and let it warm up while I'm talking. You can find out yourself. You know, just go. I think the command in Python maybe is just MD5 and the hash, and I gotta look it up. Okay, but you can calculate the hash for just about anything, and look at the string, and you'll see that it's some large sequence of hexadecimal digits, and you change the string ever so slightly, right? Ever so slightly. Maybe include just a space or a new line, an invisible character. The hash is completely different. It's not like, you know, the string changed slightly, so the hash is also going to change slightly. No, the hash changes completely. You know, it's a totally different number. So, and that's the beauty of a hashing number, a hashing algorithm, because now, even though you have input values that are coming to you one after another, where they get placed in the hash table is completely out of, you know, not related. They get placed in different locations, and it's important that happens because of other properties of the hashing table too, right? There's different hashing strategies. You don't want the, you know, clusters of objects to build up in one place, right? So there's other criteria, and all of those, you know, every one of those is. I love hash tables really because, you know, by starting to design the whole idea of a hash table like we did in class, starting from the problem at hand. The problem is I want to store a dictionary, right? Starting from there, designing it all the way, you look at every one of those problems and you know exactly why a hash table works like it is supposed to, or it's been described, right? Because people have discovered these little solutions and these little problems with the hash tables and fixed each one of those. So you have this collision, you minimize the risk of collision. So even with a good hashing function, which, you know, uniform distribution, you still have a risk of collision. Even though they may be two completely unrelated names, they could end up having the same hash. Because, you know, I got two elements that have exactly the same hash value. In reality though, it may be that you never encounter those two elements because they're not next to each other, right? So you design your hashing in such a way that the collision likelihood is minimized. It's still possible to have collision, right? But it's minimized. You get it to be as low as possible. Then you can make other trade-offs, saying, okay, well, you know, how big does my hash table need to be? Does it need to have some buffer over, you know, it's overload, the load factor in the hash? Does it always need to have some empty space, or is it possible to fill it up completely and then grow on demand? All those questions you start bubbling up, and those have individual solutions, right? So you fix those, and you get this beautiful data structure. So that essentially is your hash table. Which now what we've done is basically an entire lecture on CS2C. This is the 2C. If I was teaching CS2C and hash tables, this is basically, you know, the hash table lecture. You don't have to know any of this, but I think that knowing about hash tables, even as you're learning CS2A, helps you code better in many ways, right? Because already you're trying to make decisions as to, should I use a linked list or an array for this problem, right? And there you go, you got another data structure now to think about. You don't have to use it, but you know, a hash table. When do we use a hash table? And when do you use a, you know, so you get to think about that. and maybe later on in 2B you'll say, well, sometimes I want not just a linear data structure, but I want a non-linear data structure, like a tree, right? So every element has a successor and a predecessor, and I'll store it like that. If like in an array sorted, in a sorted array, every element has a well-defined successor and a predecessor, right? So you could say, I'm going to store the sorted array in a different way, and I'm going to store it like a tree. So I have an element, the successor goes to the right, and the predecessor goes to the left. 2 pointers. That's a tree. So see, you can come up with these data structures, and the tree will have its own use cases, right? So if you have data and you store it in a binary tree, then when you look for something, you just need to go start at the root and say, that's your item, right? And the height of the tree is logarithmic in the number of elements, because every time you split in 2. And so you don't have to descend that many levels. So all those things, all those nice, really cool things, right? I'm so excited, really, because now at the end of 2A is when you're really starting your adventure, all right? This is your adventure, and it's a hugely exciting adventure, because there's going to be so many. You're entering this this jungle, as it were, okay? And there's going to be lots of little problems, but these problems are now none of these is really beyond you, and these are just enticing problems to say, hey, don't give up. There's another interesting problem here. Come and solve me. So you're going to be facing this increasingly, and I wish I was in your shoes in that sense, because you got more to discover and learn about, right? Each one of those is a greatly fulfilling experience. Oh, that's why people have been doing it this way. That's why people have been doing it this way, right? And sometimes you may think that, people have been doing this way for 5 years or 10 years. Why don't they do it this way? This is obviously a lot more efficient, right? And then you say on Stack Overflow or some place and say, well, yeah, you should do it this way, not this way. Jessica, welcome. This is last class of the quarter. I'm glad you made it. Okay, so you say, then you publish your thing on Stack Overflow and say, do it this way, guys. Don't do it that way. And people will say, hey, let's use Jason's algorithm for hashing or something like that. Yeah. So that's your hash tables. We were talking about hash tables, Jessica, but we will talk about it again in 2B and 2C. All right. So any other questions about linked lists and hash tables? It's interesting that we had nothing to talk about today when we started, because we'd already covered all the material, and then Christopher asked a question. Yeah.
I mean, when it comes to the whole grading thing, I guess I thought that instead of doing like a dictionary, it would be easier to just store every single student as an object, and then you just have different variables for the different grades they get on each assignment.
What would I do if I needed to find Jason's grade?
You'd have to have a getter for.
What would the getter do?
The getter would.
Oh, you're saying for the JSON object you have a getter that gives me the score.
Yeah, so you have a class set up that has the variables for each assignment grade or whatever.
That's per student.
You have to have an individual class per student, or could you just make...
No, I'm asking your proposal. Your proposal is that every student is an object. Every student is an object, yeah.
And then each object has different, I guess, functions. There's like getters and setters.
Let's say there's only one grade, right? Every student has exactly one grade, right? So there's a JSON object, and in the JSON object there is a grade for 2A.
Would that be the final grade, or would that just be...
I don't know. Doesn't matter. All I need is some way of accessing your record, updating your grade, and putting it back.
You just have to have a getter and a setter then.
Yeah, but how would I getter and setter for what? For your grade or for your object? For the JSON object or for the score inside the JSON object?
You'd have to do it for the score inside the object.
Okay, good. All right, but how would I get the object in the first place?
You would have to have like a vector of objects, and then...
Right. So that's the first problem at the beginning of the class, right? So if I have a vector of objects,
yeah,
then I have to have a vector with one student per element, or one element per student, right?
Right.
So if I have a one element per student, and I'm stuck with the same problem as before, saying how do I find out Jason's object in that array of objects? I have to start at the beginning and keep comparing names until I find an object whose name is Jason. Yes?
Unless they're already sorted alphabetically.
Well, if they're sorted alphabetically, that's different. Okay. Even then, it's logarithmic, right?
Yeah.
Even if they're sorted alphabetically, I can only get to Jason's record in log time, not constant time. I want to get to it in constant time, like an array.
Oh, I see.
Yeah?
Yeah.
So that's a challenge. And that is a problem for which Jack's solution works. Right? Because now Jack said you can use an array, and when Jason asks for his score, you don't have to search the array. You can calculate a number for Jason Ballard, and then go to that index directly without having to scan for the array. So that's your hash. And then you said, Cheyenne said, what if there's a huge name, right? Then your array has to be really big, and you don't have that much space. And then you said, no, we can fix that problem. We can still go with Jack's solution, but we'll fix that problem by saying taking all the huge names and shrinking them down to like 10-letter names somehow. That's what you're doing. That's essentially what you're doing, right? Calculate a number and then divide the number by n and then multiply by whatever.
Yeah.
So that's what. So that solution still works, but it has the risk of collision, meaning that two names could have the same number. So since the subject of hashing was studied in such great detail, we were able to come up with good hashing functions, stock hashing functions. So that's why today in C++, Java, you can just say, I want a string hash. You don't have to go and define a string hashing function yourself. The library functions for hashing are actually good enough. Not always good, because in some domains, you'll find that they're bad. But most of the time, the library hashing functions are good enough for strings. If you come up with an object, a sequence of bytes, which is not like a string, then you may have to come up with a tailor-made hashing function, right? A hash for your own object. But for strings, I think the library function is pretty decent. And the string hashing function, if you look at it, gives you hash values that pretty much look random, right? Even if you give it hash A and then hash B, even though what you're hashing are next to each other, the hash values will be wildly different, two different numbers. Yeah. If my computer is, if this is come up, I can show you, right? Anyway, so that's the difference between the different kinds of data structures you use. Are you now like what's the word for it? Are you now appreciative of hash tables now? Because people use hash tables and dictionaries in Python, because it's such a convenient and easy data structure to use. But I always say what makes a good programmer is not being able to use things out there, but using things with being aware of what they do and what the difficulties are of what were the problems faced in the design of that thing. If I use that, what is the risk? And is that risk there, or did the designers of that class were they aware of the risk, and did they already build in the? And most of the time, when you use library functions, you can be confident, right? Because we're talking about programmers. Programmers are intelligent people, right? You guys know you're programmers. So programmers have a way of thinking about things, way of thinking about life, way of minimizing resources. Because programmers are software engineers, right? Engineers always try to build things with the least amount of resources, right? Programmers, our resources are compute cycles, right? So if you're a software engineer, you're trying to build the software products with the least amount of software, compute cycles. But not just compute cycles, right? Storage is also a resource. But I think that you translate them all into some unified resource unit, right? So in a computer scientist would say, I want to do this, but in the least amount of resources. But a non-computer scientist can still solve a problem, small problems, right? So they can solve small problems using sophisticated data structures. So that's the risk in the Bay Area. Everybody thinks they can program because we're in the midst of these great companies, right? And they say, well, I'm going to learn Python, and they say I'm going to use a dictionary for this. I'm going to use this. They use really sophisticated data structures, and sometimes when they don't need to use that. Sometimes a simpler data structure like a plain array might actually be more suitable and more efficient. just by throwing all these sophisticated things together, you don't get a better product. And so, because Python and JavaScript, and they make available these things, they say, I'm going to throw in a dictionary here. And throw in no, that's not the way to do it, right? You got to know why you need a dictionary and what the risk is. What the risk is. You know, you can, if you can use an array, especially if the data you get is already sorted, right? Yeah, or sometimes you just use a bit field, a bitmap, right? So, yeah, and then you say no, you know, very minimal overhead. You just, if you're just going to store true and false values, why use an array, right? So those are the kinds of trade-offs. And that's how you become an engineer, not a you know, run-of-the-mill coder, right? Because coders are engineers. In the Bay Area, programmers, coders, they're all engineers, you know, software engineers. But you're not really an engineering programmer unless you're thinking about it with an engineering mindset. And an engineering mindset is, how can I do this with the fewest resources I can, right? Which also makes you, if you design a product, you know, if a good engineer designs a product, that engineer is able to sell the product for the least possible price and still make a profit, right? A bad engineer will design a product, maybe the same product, but they cannot sell it as cheap as you are able to, right? Because they have to use more resources to do the same thing. That's why Amazon is like killing everybody, right? Because Amazon looks at the problem from an engineering mindset. You know, Google, Microsoft, all these guys, you know, software is killing the world because they're looking at it through the engineering perspective. And say, well, you know, all these things I can do with fewer resources, and I'm not greedy. It's not just the engineering mindset. I think this engineering mindset coupled with the do no evil mindset also, right? Because you can say that I'm just going to be a really good engineer, but I'm also not going to be that do no evil guy. Then you say, I'm going to do everything for the cheapest cost possible, but I'm not going to sell it for the cheapest cost possible, right? I'll pocket the difference. So you have your competitor selling at the same price. They're making less profit because obviously they're doing things in a, you know, really inefficient way, and you're doing things in an efficient way, but you're selling at the same price as that guy, right? So that means you're a solid engineer, but you're not really a good, successful. You know, you don't have the complete mindset to make a successful product because you're not undercutting the competition when you're able to, or you're not passing on the savings to the consumer. Yeah, I think that's what it is, right? So the Amazon mission, and also all the tech companies. Google gives you search for free, right? So the Amazon, I think the motto is that we're going to do things in the best possible way, and so it doesn't cost us a great deal of money, but we're not going to go off and party in Vegas. Well, right now they're partying in Vegas because it's the reinvent, but you know, but other companies party in Vegas all the time, right? But you know, Amazon says, you know, we've had a hard year's work. Let's now party and celebrate what we've done. But they don't do that, right? They don't take these huge paychecks and say, wow, you know, we got a lot of money. Say, well, how we got all this money now? How can we now reduce the price of all the things we sell so that the end user benefits, right? So that's why you go to Amazon, you gotta find these cheap products. Eric?
Well, now Amazon does like a lot of the market stuff, so they don't sell the stuff like directly from them anymore, where they like just provide the shipping basically for like.
Oh, I thought they were doing that for a long time. You know, that was what, the affiliate program or something like that.
Yeah.
Yeah, they.
I noticed that the rise of the, like, you know, the smaller marketplaces kind of coincided with like Amazon's surge in popularity.
Oh, the smaller ones went down. You mean? They died off.
No, like, you know, like random people that are selling like
Uh-huh.
phones or something from like companies that you would have never heard of.
Oh, they're selling on Amazon now.
Yeah, they're all selling on Amazon as opposed to where I believe they used to be on eBay. And like there's still people that do it on eBay.
I don't know,
but there's
yeah.
like a credibility element, I think, on Amazon too. So
Possible,
I think
yeah.
part of the reason they do all that and like kind of eat the cost in terms of shipping or just have
Yeah.
you know, all the stuff like in the warehouses and everything like more local.
Yes.
How to do like local prime stuff, right? Which is it's like the added benefit of having the mind share and the market share.
Yes.
Because like I think
The branding is they're leveraging the brand. Yeah, I don't know. I'm not keeping up with that side of things. But I'm just, you know, I'm just confident, and I trust all the tech companies to come up with, you know, do things that are good for us.
yeah, but I mean I know you remember a time when eBay was the only way to really
Yeah,
do it,
yeah.
and how many shady things may not have gone through eBay. eBay or
Yeah.
may not have worked out.
I've bought a lot of products on eBay that didn't work out.
Yeah.
So yeah, 3 weeks ago, last month I ordered. I was just randomly browsing and something popped up on my screen saying a 3 terabyte USB stick, right, for $15. For $15, right, 3 terabytes. And unthinkingly, I just said, okay, well, let me order that and see what the hell is going on, right? So I ordered it, and then I was talking to my son and he said, are you like out of your mind? You don't even think, like, is it possible before clicking buy? And it arrived, and I checked it, and turns out that it slows down as you're copying data to it, right? And after about 2 gigabytes, it slowed down so much that it wasn't really worthwhile waiting for it to complete. So, but anyway, so I've had that problem. But you know, you have that problem also on Amazon. So you look at the reviews,
Oh, yeah.
right?
But Amazon has that. They have better like assurances and stuff like that. 'Cause,
Mhm.
like for me, for instance, like my mom really is adamant about having a bunch of like ink like at the house with the printer.
Yeah.
Like not like just like one extra cartridge. We're talking like a couple extra.
Right.
So we have to order like a bunch in advance. And like a lot of them come from like different Chinese companies.
Oh, I see.
And then like they have the like different chip on the back of it than the one my printer actually.
Oh, so the printer didn't recognize it?
Didn't recognize it at all, and of course, like because it's like a stock, like I didn't check it until I needed it months later, and then afterwards, I just contacted Amazon, and they're like, "Oh, yeah, it's cool. Like, we'll just refund you and you
Yeah.
just throw it away." As opposed to like eBay, where they would have just been like, "Should have checked it in the first 30 days."
Yeah, that's too bad. But generally, I'm more trustful of the tech companies than some of the other non-tech companies.
Oh yeah, 'cause, like if you're just buying it, like I would even say like I think Newegg used to kind of do the same thing.
Yeah.
But, like even then, like there was still certain marketplaces through Newegg that I was kind of like about,
Yeah.
And it's one of those things that like I enjoy the fact that Amazon kind of has like taken that place for us because it kind of beats having to like go to Target to like,
Yeah,
buy
yeah,
like
yeah.
toothpaste or something like that.
Well, now you can go to any retailer online.
Oh yeah,
right?
and they kind of force the market